Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Naver Cloud HyperCLOVA X 8B Omni, an any-to-any omnimodal model. HyperCLOVA X 8B Omni is an 8 billion parameter model that can both understand and generate text, images, and audio. Instead of stitching together separate models for each modality, it uses one unified backbone to handle everything. The team releases its weights under a license that still allows commercial use, and they put special emphasis on strong performance in both Korean and English. Modern AI systems are increasingly embedded in real products, assistants that see, listen, and speak. Those settings naturally involve text, images, audio, and often video. Relying on text alone misses a lot of real-world information, and we're already hitting limits on how much high-quality text we can collect. A common workaround is to bolt encoders and decoders onto an existing language model, but that often causes catastrophic forgetting, where the model's original language abilities degrade. HyperCLOVA X 8B Omni is designed to avoid that by training all modalities in a unified way from the start. The key promise of HyperCLOVA X 8B Omni is any-to-any interaction. You can go from text to text, images to text, text to images, speech to text, audio to text, and even speech to speech. Text-to-speech is also built in. Importantly, all of this runs inside a single model, rather than a fragile chain of separate systems. That makes it easier to deploy and to reason about its behavior. At the heart of Omni is a decoder-only transformer, similar in spirit to a standard language model. The twist is that it doesn't just predict the next text token. Instead, it predicts the next token in a mixed sequence that can contain text tokens, visual tokens, and audio tokens. Vision and audio each have two faces, discrete tokens that the backbone can auto-regress over, and continuous embeddings from modality-specific encoders that inject fine-grained perceptual detail. This shared next token interface is what lets the model seamlessly compose information across modalities. The backbone is a 36-layer autoregressive transformer with a hidden size of 4096, closely following the HyperCLOVA X Think model. For text, the team uses a tokenizer that respects Korean morphology while still being efficient for English, code, and math. They also use a multi-token prediction objective, which adds an auxiliary head that predicts several future tokens at once. That increases the amount of supervision per token without changing the core next token objective, making training more efficient for an 8 billion parameter model. For images and video frames, Omni uses three coordinated components. A continuous vision encoder based on a vision transformer extracts dense features aligned with the language model's space. A separate semantic tokenizer converts visual features into discrete tokens that the autoregressive backbone can model, focusing on high-level semantics rather than raw pixels. Finally, a diffusion-based vision decoder turns predicted tokens back into images. This setup is tuned for a relatively compact 8 billion parameter backbone where you want tokens that are both information-rich and easy to mix with text. The model reuses TA-Talk, a text-aligned tokenizer that quantizes patch-wise visual features into discrete tokens and can reconstruct them. TA-Talk expects 384 by 384 inputs, so non-square images are resized, tokenized, decoded as a square, and then resized back. The authors show that the resulting distortion is modest and can be compensated by training a decoder that is aware of this pipeline. Their diffusion decoder conditions on the reconstructed visual features via channel concatenation rather than attention, which speeds up convergence and supports near-native aspect ratios while keeping compute manageable. On the audio side, Omni again combines continuous and discrete views. A frozen encoder derived from Whisper Large V3 converts 16 kHz audio into log-mel spectrograms, and then into 25 Hz continuous embeddings. In parallel, a separate tokenizer based on finite scalar quantization turns speech into discrete units at the same 25 Hz rate, giving a codebook of 6,561 tokens. For generation, the unit Big VGAN decoder takes these discrete tokens plus a speaker embedding extracted by an eKappa TDNN model and upsamples them into a time domain waveform. Each token corresponds to about 40 milliseconds of audio, which keeps sequences manageable. Long videos with audio can easily blow up the context length. To handle this, Omni compresses continuous audio embeddings from 25 frames per second down to 1 frame per second when audio is interleaved with video. They do this with a lightweight Mamma Mia state space module placed after the audio adapter. This dramatically reduces the number of audio tokens in long sequences, making video-centric tasks feasible without sacrificing the overall context budget. Throughout training, the audio encoder itself stays frozen, leveraging its large-scale pre-training. Training Omni happens in stages. First, the team pre-trains a strong text-only backbone using a carefully filtered and partly synthetic corpus in Korean and English, with increasing context lengths up to 32,000 tokens. Next, they expand the vocabulary to include discrete vision and audio tokens and perform large-scale multimodal pre-training. Only after this symbolic interface is stable do they plug in continuous vision and audio encoders and align them with the backbone. Throughout, they use curricula and loss masking to prevent the model from forgetting its text skills as visual and audio tokens flood in. The discrete token phase has 3 main stages. In stage 1, they expand the vocabulary with vision and audio codebooks, but freeze the text embeddings and LM head, only training the new modality embeddings. This protects text performance while the model learns what non-text tokens mean. In stage 2, all parameters are unfrozen for a 2.3 trillion token multimodal run, with a tuned mixture of text, images, and audio and a temporary downweighting of vision loss to avoid overwhelming the backbone. Stage 3 is a brief long context adaptation, focusing on multimodal sequences up to 32,000 tokens. Once the discrete interface is in place, the team aligns the continuous encoders. For vision, they first freeze both the backbone and the encoder, and train only a linear adapter on image caption, OCR, and VQA data. Then they unfreeze everything and run a large vision-centric stage that includes both understanding and generation, plus image editing. Editing is especially useful because it forces the encoder and tokenizer to agree on how images are represented. Finally, they integrate the continuous audio encoder by training a small adapter on ASR tasks, completing the omnimodal architecture. Pre-training gives you a powerful but raw omnimodal backbone. To turn it into a usable assistant, the authors run a 4-stage supervised fine-tuning pipeline. They begin with text-heavy conversational data to lock in dialogue skills and reasoning. Then they ramp up multimodal instructions, add long context and video-centric tasks, and finally teach the model to perform explicit multi-step reasoning. They deliberately avoid reinforcement learning in this work, aiming first for a robust, supervised baseline that already handles complex cross-modal queries well. In stage 1 of post-training, the model learns to be a conversational assistant while also seeing basic multimodal tasks like captioning, ASR, TTS, image generation, and editing. Stage 2 shifts the balance toward rich multimodal instructions, especially challenging image understanding. Stage 3 focuses on video and long-range temporal reasoning, including an audio token compressor for efficient video handling. Stage 4 introduces an explicit reasoning format using a think block, where the model first classifies user intent, chooses which modalities to use, and then carries out multi-step reasoning before producing the final answer. To evaluate Omni, the authors compare it against a range of open models of similar size, including Qwen 2.5 Omni, Emu 3, Janus Pro, X Omni, Step Audio 2, Qwen 2 Audio, and Audio Flamingo. Across text, vision, and audio benchmarks, Omni is consistently competitive and often best in class, particularly on Korean datasets. Crucially, it's the only model in the comparison that supports every major input-output combination across text, images, and audio, so it delivers broad functionality without sacrificing quality. On pure text benchmarks, Omni shines. It clearly outperforms all comparison models on Korean suites like KMMLU Pro, Hare, and Cobalt, showing that the Korean-centric data and tokenizer design paid off. In English, it achieves top or near-top scores on MMLU, MMLU Pro, and GSM 8K, indicating solid general knowledge and math reasoning. On the Flores Plus translation benchmark, it leads in English to Korean and is competitive in the reverse direction. The performance gap is especially pronounced in Korean, underscoring its strength as a bilingual model. For vision-to-text tasks, Omni performs very well. On Korean benchmarks like KONET and KMM Bench, it achieves the best scores, and it's second best on KDTC Bench. These datasets cover educational reasoning, diagrams, and diverse visual language skills in Korean. In English, Omni leads on Seed Image and LAVAW, which tests general visual question answering and multimodal reasoning, and remains competitive on text-heavy tasks like text VQA and doc VQA. Overall, it shows that the model can align visual content with language across both everyday and structured documents. On text-to-vision tasks, Omni is particularly good at image editing. It achieves the best score on the Image Edit benchmark, which measures how well models can modify images according to text instructions while preserving the rest. On GenEval, a general text-to-image benchmark, it ranks third but still competitive. Qualitative examples show that it can generate consistent images from semantically equivalent prompts in English and Korean, and that it can incorporate Korean cultural elements into its outputs. Its editing examples demonstrate style changes, object removal, and background replacement with good semantic control. Because Omni's vision encoder is shared for images and video, it can handle video understanding tasks out of the box. On the Video MME benchmark, evaluated without subtitles, it scores in the high 50s, comparable to GPT-4V and ahead of some popular open models, though slightly behind Qwen 2.5 Omni. On an internal Naver TV benchmark of real Korean video content, it significantly outperforms GPT-4V. This suggests that the Korean-centric multimodal training helps the model grasp both temporal structure and local cultural context in video. On audio tasks, Omni is very strong, especially in Korean. It achieves the best word error rates on Korean ASR benchmarks like Kspan Speech and Florsco. In English, it's slightly behind Audio Flamingo 3, but still competitive on LibreSpeech and Floors. For audio captioning on Clotho V1, it reaches the second highest Spider score, showing it can describe complex sound scenes. In speech-to-speech translation between English and Korean, evaluated via ASR Blue, Omni tops all compared models in both directions, demonstrating that its unified architecture can handle direct spoken-to-spoken translation effectively. To assess text-to-speech, the authors ran a mean opinion score test with 30 human listeners, comparing Omni against commercial systems like Gemini 2.5 Flash, 11 Labs GPT-4o Mini TTS, and Qwen 3 Omni 30B. In English, Omni's naturalness scores are close to the best systems. In Korean, it actually leads the pack, achieving the highest MOS with tight confidence intervals. Listeners rated it as generally natural and easy to understand, indicating that its TTS quality is not just research grade, but ready for practical deployment. This slide highlights the central achievement of HyperCLOVA X 8B Omni, a single unified model that can flexibly move between text, images, and audio in any direction, while remaining compact and open enough to be widely adopted in research and industry. Despite its strengths, Omni has clear limitations. At 8 billion parameters, it can't match the absolute performance of frontier-scale models, especially on the hardest reasoning tasks. The semantic vision tokenizer operates at a fixed resolution and requires resizing non-square images, which inevitably loses some detail, even if the diffusion decoder recovers much of it. The current work focuses on supervised fine-tuning rather than reinforcement learning-based preference alignment, so there's room to refine its conversational behavior. The authors explicitly see this model as a pathfinder and plan to scale the architecture up to larger, more capable omnimodal systems. HyperCLOVA X 8B Omni demonstrates that a single decoder-only transformer can serve as a true omnimodal engine, handling text, images, and audio in both directions through a shared next-token interface. With carefully designed tokenizers, encoders, decoders, and training curricula, it achieves strong performance across Korean and English, and across understanding and generation tasks. Its open weights and relatively modest size make it a practical starting point for both academic work and real-world applications that need rich, multimodal assistance.